as the president said, the talk is about something that sounds like out of this world, and it really isn't. It's about very simple informatics, and you will get to see that in a little bit. First of all, another connection to astronomy, maybe, cosmology. This is a very famous computer scientist, Edgar Dijkstra. He won the Turing Award, which is the informatics version of the Nobel Prize. We don't have Nobel Prizes in informatics, and he won basically the highest award in informatics. And he once said this: so computer science is no more about computers than astronomy about telescopes. So think about that a little. So basically, if an astronomer or somebody doing research in astronomy, if you think that's a guy who actually screws around on the telescope, adjusts the telescope, knows the newest model of all telescopes, has a lot of telescopes at home, that's not really an astronomer, right? In the same way, computer scientists, certainly we have computers like everybody else. But I think the actual thing that we do is not so much like installing and fixing computers. So I'll try to show you now like one little sliver of computer science. I try to explain it for everybody, so I hope the computer scientists among you will not be bored, but we'll see. So computer science, I'm using that as a synonym for informatics. So we are the faculty of informatics, and for me this is really the same. Informatics, computer science is the same. What is it? I think a big part of computer science is math. So to some degree, we're all mathematicians in some way. But it's maybe not the math only, the math you learn in school, but there's a lot of things like logic, for example, in there. Sometimes you're more philosophers than mathematicians. So math is important. Another big contributor is engineering. So at many universities, the computer science department is part of the College of Engineering. So there's the mechanical engineers, electrical engineers, and then computer engineers and computer scientists. As an engineer, we're building stuff, we're creative, we kind of explore stuff and construct things. And we, of course, do that in a principled way. We don't just play completely. We're playful, but we don't only play. We have a plan. Another factor is science. So it's called computer science, and there is certainly a science part to our science. So we follow the scientific method. We formulate hypotheses, we test them. We have a lot of experimental scientists in computer science, but also theoretical scientists who come up with new models of thinking about computation. Now, this is probably what most people would kind of associate with computer science, but there is another factor that almost nobody in the public might mention, but it's an extremely important factor, and that is social competence. So that is an important part of our faculty. It's front and center in our teaching at the informatics faculty. Our students start to develop projects in the first semester. They collaborate, they present. And this is for a reason. It's not just because it's fun, but it's for a reason. And I'll try to show you why that is important in a bit. So that's the global area of computer science. And now what I do is just a small subset of that. So here you have a person. That's a software developer, a computer scientist in industry, and you have a computer. And in between those two, you have the area of programming languages. So this is about languages in which you can talk to a computer and order the computer to do something. So you give instructions to a computer in a programming language. The language should be understandable for humans, but it should be executable by the computer. So this is quite tricky. It's kind of similar to human languages. It's like Italian or English, but we call our languages like C or Java, but it's a language. The second area that my research kind of goes into is software engineering. So this is more on the human side. It is how can people develop software systems that actually work, that fulfill the purpose, that are fast, efficient, and all those different qualities we attribute with software. So software engineering is not that we, the researchers, sit down and write software. It's that we study the process, we build tools and methodologies to help people build software that works. And the last circle in which I move around is the systems. So that's more on the computer side. And here, we try to make it possible that those programs that software engineers write, that they can be efficiently executed on a computer. So we build operating systems, we build runtime systems for programming languages, we build database systems to store your data, we build distributed systems to move data around. So that's the systems area. And my research is kind of, I'm moving around in those areas. So, to the body of the talk. I grouped the talk into several acts, and I want to start with Act 1, which is on complexity. I think that's really important. So, who knows this? Who has ever seen this software? Okay, there are some people, very good. So you have iOS 7, I guess, on your iPhone or iPad. This is the Maps application from a mobile phone, and it helps you find your way. This is software. But if you look at it from a little bit closer, you see that this is very small. This is just the user interface of software. So as a user, you see just the display and some pictures on the display. But in reality, as you know from icebergs, the biggest part of the iceberg is under the water. And that underlying system is really big, and it's invisible. So I can't show you a picture of maps except for the user interface. Unless I show you pictures like what Professor Lanza is creating, which are beautiful pictures you have to look at one day. Okay, so we have the underlying system, which is really big, and the user interface, which is also quite big, but together they form something that's really large. And now the question is, what do I mean by large? Let me try to find an analogy for that. Who has read this book? One? No, okay, more than one. I've read it a long time ago. It's the first Harry Potter book, Sorcerer's Stone or Philosopher's Stone if you're from Europe, and do it in English. So, how many lines of text are in this book? Lines, not pages. Any guess? 100,000 lines. Okay, let's try. I did it in a clever way. I counted the pages, and I counted how many lines per page, so I didn't have to go through everything. So we'll have 8,600 lines. So it's quite a lot of text. And the author of the Harry Potter series, J.K. Rowling, had to come up with a good story to drag you in so you would read the whole book. It's not at all repetitive. Like you start reading and you cannot stop. It's a really exciting book, at least for me it was. And I think for many other people too. So, this is a book. And I guess we all agree that this author of this book did a great job. It was not simple to do that. Now, who knows this? Okay, how many of you have no account on Facebook? Wow, okay. I thought I would only see Antonio Carzaniga, but okay. Even the president has no account. Okay, so I have one, I rarely use it. So, how big do you think is Facebook in lines of text? Now, I'm not talking about all those messages that the Facebook users, the billion of Facebook users write. I'm talking about the programs that make Facebook run. How many lines? We have this, 8,000. How big is Facebook? Million? Yeah, kind of close. 9.2 million lines. According to this source, probably it's much bigger already, I don't know. This is hard to find out, really. So, who knows this? I hope all the computer science students know this. This is the coolest operating system. Linux. So how big is Linux? And I mean not just the Linux kernel, but the whole thing. If you get a CD of Linux, how many lines of text is Linux, the source code? 200 million. Ooh. Okay, a little bit overstatement, but yeah, 13 million. And the last one I'm going to show, the last piece of software, is this. This is what's running on my notebook. It's Mac OS X. It's an old version of Mac OS X. because I don't know any numbers for the current version. How big is that? We had Linux. Linux was 13. 50 million. Okay, quite close. 86 million. So think about it again. Somebody had to write all those lines of text. Now, they're not written in English, but still, they're written in a language, they're readable by humans. So this is a bar chart. On the x-axis, you see the size. In this case, Mac OS X is 86 million lines. And if you compare it to Harry Potter, I think you cannot see the bar. It's less than 1 pixel because it's only 8,000 lines. It's a linear scale. So I've heard that J.K. Rowling spent 5 years writing this first book. She didn't just spend 5 years on this book. She also planned the entire series, but still, assume that it took 5 years to write this. How long will it take to write Mac OS X? 50,000 years. So I don't think we can have a student who goes and writes Mac OS X sitting there for 50,000 years. So that's why we need collaboration. That's why it's essential that people can work together in informatics, that they know how to structure a really, really large project. So maybe there are some hardware people here, some hardware engineers or people who like hardware. So you would probably make a statement that, okay, you say that million, that's big, but if you look at hardware, that's really big. So let's see. This is a piece of hardware. It's the processor that's in my computer. It's a Core i7 processor from Intel. And this processor has 9.2 billion switching elements, transistors. So billion, that's really, really large. Or this here is a bridge. It's called the 7-mile bridge, and it's 7 miles long. So that's really large. Now, my point I want to make is, yes, I agree, hardware is even larger than software in some way. I can't tell you how many lines of text, but I mean, it's large. But if you now look at it, this bridge is repeating the exact same sequence over and over. There are 264 spans. So it's copy-paste. You create one of those spans, you design one of those spans, you think about it, you simulate it, and you can just replicate everything. And this replication is even bigger for our CPU. So this has a cache on the CPU, so memory, and you have 100 million times the same storage element. So you design that once, and then you say we need to copy-paste that 100 million times. So that makes it much simpler. It's not generally simple, but it's a good reason why it's not really 9.2 billion, I don't know, lines. You have to divide by a big number. So that's hardware. And when you build hardware, you have this kind of assembly line, like when you not design, I mean, you know iPad, designed by Apple in California. That's the kind of intellectual contribution. And then it's manufactured, where you create many, many, many copies of the same thing. And that's the kind of industrial version where you build it on an assembly line. For software, this doesn't work. So in software, you have no replication. No replication. I mean, we just had an argument today, and some PhD students would disagree with me, I'm sure. So don't take this as a proof or a formal claim, but the goal is to have no replication in software. My goal. The students who take my course, they know. So if you look at one piece of software called Firefox, which many of you may run on your computer, a web browser, the most recent version of Firefox is written in several different programming languages. And if you look at how many lines of text are written in C, it's 18,000 files, actually not lines, files. In JavaScript, 16,000, Python, 1,200. So a lot of files. You could think about those files like documents or maybe a chapter of a book. So there's a lot of chapters of books in this software. And the point is, every single file is different. It's like in Harry Potter. You don't read chapter 1, and then you go to chapter 2, and you read the exact same thing. It should be different. And that's the same with software. Every piece of code you write should be different. So if you don't have this replication, it's really difficult to write software. Software is really complex. And together, those two aspects, software is large, millions of lines of text, and software is complex, no replication, this is a big problem. The problem is that you cannot do that correctly. I mean, no human being can write 86 million lines and not make any mistakes. So there will be mistakes in software. That's our problem. So now, to the more of a body of this talk, there will be mistakes, and we call them bugs in informatics. And I want to show you a bug, or how that looks, a bug, and how we can catch that bug. And you'll learn why we need alternate universes or time traveling, how that helps. So first, who has ever seen something like this? Very few people. So some other versions of this, I'm sure people have seen. The blue screen of death. If you have Windows and your computer crashed, you've seen something like this. This is a modern version of it. You may have seen something like that, or that, or that, or that. Like, those are normal messages as a user you get when your system crashes, usually because of a bug. So there's lots of bugs in the software that you use, and you're a bit annoyed every time your computer crashes. Now, bugs are worse. This is annoying, but bugs can be pretty problematic. Let me give you a couple of examples. For example, the Bank of Queensland in Australia had an entire week downtime of their payment terminals. So imagine if Switzerland had no ATM working, Postomat is not working, Bancomat is not working, you can't get cash for 3 weeks, 4 weeks, what happens? I don't know. So, other one, power grid. I was in the US, I lived there at that time, 2003, when they had 55 million people without power for 2 days, and I can tell you it was really hard to get around in New York because no metro or train was running. This one was probably not much recognized, but there was a problem in a library of encryption software that is used in several, probably browsers and such. And it was the software that generates random numbers, which are important for cryptography, was compromised. And so it generated very weak keys. And that means if you did banking transactions using this software, it was probably quite easy for somebody to see your credit card number and to track what you're doing. So this is not good. That was a bug. And they fixed it, but only after about 2 years, I think. And this is probably some of the worst thing that can happen. That's a long time ago, but those radiation therapy machines, they had a bug in the software, and the dosage of radiation treatment was way too big, and people died. Not just one, several. So you want to catch those bugs quickly and avoid big problems. So there's a Wikipedia page. You can find more bugs, and there's tons of stories on bugs. So now, what do I mean with bug, and where can you find such a bug? For that, we have to go and look at a program. So that's how you tell a computer what to do. You write a program. And here I'm showing you a program in a somewhat visual language. You call that sometimes code a program or instructions. And instructions, really, they are. So every box you see here, every line is one instruction to the computer saying, do this. And a program is a sequence of instruction, meaning you do the first one, then the second one, then the third one, and so on and so on. Okay, you start at the top and you work your way down. There are some instructions that are a bit special. We call them branch instructions. So when you execute such a branch instruction, you look at something, you take a decision, and depending on what you decided, you go to the next instruction here or to the next instruction there. So you branch out. Now, what happens in this particular program? Let me give you the high-level overview of what this program is supposed to do or what it means. Like many programs, at the beginning, we set up our stage. We get ready to do some useful work. So this is the setup phase where we do 2 instructions, and you'll see them executed soon. Then we need to do some input. A computer program processes some data, so we need to get that data from somewhere. In our example program, our data are pens, pens or whiteboard markers we will use. Then we do some processing. So we take that input and we process them in some way. In our case, we are sorting those pens by their darkness. So we have the brightest, medium, darkest pen. That's what happens in those 6 instructions in the red part. And finally, we need to provide the result somehow. You need to communicate to the user, to the outside world, to you, what happened. And what we will do here is we will write USI on the flip chart here, first with the brightest pen, then the medium pen, then the darkest pen. So that's the way this works. Now, this was the code. Any computer program always has code, the instructions, and data, where you store your state or your values. And in our little computer, we have 3 such values or variables. You see them in the green box called P0, P1, and P2. You also see them here in front in this little toy, you could say. You have P0, P1, and P2. So the 3 boxes in my picture are empty. Here we already have some state in there. Now we have instructions, we have data, and we need to have something like a computer or something that executes those instructions. And for that we need what's called a thread. In computer science we talk about the thread of control, which goes from instruction to instruction, like a red thread through your picture here. And now I need somebody who acts as such a thread, and I have this kind of job advertisement. We're looking for a human subject, so one of you, to act as this thread, and here are the requirements. First, like in any computer, you need to be absolutely reliable. I mean, you cannot make a mistake when you're a thread, because there is an instruction, and the computer will execute that instruction without mistakes. The mistake is in the program, not in the computer usually. Okay? So we have some extra requirements because, as you see in the title of this lecture, we're talking about time traveling and such. So whoever is going to be the thread for us today has to have some interest in time travel because, yeah, it's better. Then also, I think, some understanding of time travel. And with a PhD in physics, that would be a good thing. And then now we get to the more problematic things. So you should be okay traveling back in time. And there's the alternate universe part also of the lecture. So you should be okay being cloned. Now, there's a disclaimer. I'm not taking any responsibility. Okay? So I've already pre-scouted a little bit, and I think you know that there's one candidate in the room. This person here. So, Mr. President, could you please come forward and act as a thread on this state or this data, and we'll go step by step, and you'll always see the green box, and right now you don't need to do anything. This is the initial state, green box, this thing. There are 3 blue pens in there, 3 blue pens in here, okay? Nothing to do yet. Now, we will say first instruction. So you have to execute the first instruction, which says walk to the table. Okay? Yes. No touching, no changing anything. So what is the state now after this instruction is executed? Nothing has changed, right? I mean, you have 3 blue pens in there. And now let's go to the second instruction. The second instruction says empty all 3 variables. Remove the blue pens. Okay, great. So the state afterwards should be empty. And we move to the next instruction. So now it gets a bit more complex. We have an assignment statement here. So we need to go to Andrea, who is a PhD student here in the front row. And you have to get a pen from Andrea and store that pen in variable P0. Could you please do it? Okay. So the state should be, after this instruction, the state should be P0 contains a blue pen. Let's see whether that's correct. Yes. The next instruction, please go to Louis, another PhD student in my group, and get a pen from him and store it in P1. Great. So the state is now blue in P0, black in P1. We get to the third instruction. Please go to Dimitri and get a pen from him and put it in variable P2. Yeah, good. So we have a yellow pen in variable P2. So now all our variables have some pens in there. And we finished our input phase. Okay, we're ready to do some computation. And our computation is called bubble sort. So computer science students should see this picture and should immediately cry bubble sort. So these are 3 comparisons and 3 swap instructions. So first instruction, could you tell me, not touch anything, just tell me, is P0 darker than P1? Is blue darker than black? No. No. Okay, so no means false. And so we go down the arrow that's labeled false, and we'll end up at instruction 8. We don't execute instruction 7. We just skip it. So now, instruction 8, again, we need to test something, not touch anything, just check P1 is black darker than yellow. Yes. Very good. Okay, it works very well. The president's great. Great. Okay, now we branch. We go somewhere else. It was a true, so we need to swap 2 pens. So could you swap P1 and P2? Okay, so let's see whether I was correct. Yeah, in the middle is yellow. Good, so we can go to the next instruction. This is again a comparison. Is blue darker than yellow? Yes. Good, so you can go to the next instruction. The next instruction says swap P0 and P1. Good, let's check. Yes. Okay, so we are finished with our sort. And if you look on the thing or look up there, you should see that there is yellow, which is the brightest in P0, and black, which is the darkest in P2. That's not magic, that's computer science. So now we go on, and we have to do the next instruction. Could you take the pen that's in variable P0 and write on the flip chart USI to market our great university? Doesn't work. Sometimes things are broken. So this was a problem. Okay, this was a failure. Yeah, you can give it to me. I collect broken pens. So this was a failure. This is a bug. This is when you have a blue screen in your Windows or an error pops up. In informatics, we call this a null pointer exception. He tried to dereference it, and there was nothing there. The pen is gone, okay, the thing inside. So now we have a real problem. We have a crash, and we would like to find the cause of this crash. We would like to know, why did this happen? What happened? Who is responsible? Where did this broken pen come from? So that is not so easy. Essentially, this is the question we ask. Where is this bug? And to do that, we have to somehow think, what did just happen? You have to try, like, where did I come from? What was in there? Reason backwards. And I think you now see the connection to time travel. So we have to think backwards in time. We're at the end of our program, and it crashes, and we need to see what happened before. So let's think for a little bit. Let's think for a little bit. So you can now say, let's just execute the program in reverse. We have all the instructions. We turn the arrows around, and we go back. Easy, no? Not so easy. We're at instruction 12, the green one, and now we need to go back. But where? Did we come from instruction 10 or 11? I mean, you may remember, but the computer only knows what is in the green boxes. That's the memory. The computer is not intelligent. It just knows what's stored there, and we don't see where it came from. So that's the first problem. There's a second problem with back-in-time execution. If we are at instruction 5, where we just put the yellow pen in variable P2, and we need to go back in time to instruction 4. What was in variable P2 now, in instruction 4? Do you remember? You can't. So you've deleted what was there, and the data is gone, and we don't recall it. So we need some help there. And one of the ways to solve this is to keep a logbook wherever we execute something, we mark that in our logbook so we know what we did and we can go back in our logbook. So here is a logbook. For every variable, for every instruction, we have a little cell in our spreadsheet which we fill in whenever we execute. And then, when we have our log, we can reason backwards. The problem with that is this is really big. So you have variables times time, at least in the extreme case. You can optimize this, but variables times time. And now, do you know how many variables you can store in a computer? Let's say your iPhone 5S, or maybe not 5S, iPhone 4. This is a 32-bit computer, so you can store up to 4 billion bytes, 4 billion bytes. And do you know how many instructions you may execute every second in a computer? Millions, billions actually. So you're about 2 gigahertz to maybe 4 gigahertz, so that's 4 billion cycles, and you can maybe do an instruction or half an instruction per cycle. So this is extremely massive, the amount of data. You need a Google data center just for this little program. Not exactly, but something like that. So this is too big. We cannot do this. I cannot say I'm running the Bank of Queensland ATM and I'm logging everything that happened in a log so that if something happens, I can go back in the log, because you need a data center just for this one machine to store everything. That's not good enough. So the log is too big, and we have to log so much that our program will be too slow. And now we come to the alternate universes. So maybe we can think about physics a little bit and say, well, if you want to enable time travel, maybe we could have another universe. Maybe that would help. So let's see. We now have to rerun our scenario. So the president will have to execute the thing again. Unfortunately, I have to quickly reset the state here. So we'll put this blue. So we'll start from scratch. Everything is blue, and the first instruction is please walk to the table. Great, nothing has changed. Now the second instruction, please empty the table. It looks pretty much the same as it just looked, right? Now the next instruction is please, let's go to it. Please go to Andrea and ask him for a pen and store that pen in variable P0. Great. Let's see. Yes. Now we go on. Oops. Okay. So let me now say that our president and this little memory here, that's a universe. Okay, you see the galaxy there somehow. So that's a universe, a thread and a piece of memory. And if I want to clone that, I have to create like a copy of the current state of the universe. Now is the dangerous part. He's signed up for it. I don't know how we'll survive that, but we'll try. So we have to clone the universe and create another universe with the exact same state. And I tried really hard. I haven't figured out how to do that, I have to admit. So I can clone the state here. So Mohammed is actually a PhD student who is implementing this for real. I mean, not with these toys, but for real, as software for doing debugging. So here we have a clone of our state, and now we need a clone of the president, and we need somebody, well, who is very similar. So, is there another president in the room? Ah, yes, okay, I planted him here. Yeah, so we have our former president, Bargiolini. Could you please come forward to the table? So, your alternate universe, which is this one. Thank you. Okay, so we have cloned this, and this is actually, if you implement that for real in software, this is not so easy to do this cloning. In particular, if you have multiple threads, it's very difficult. You can talk to Mohammed how to do this. He spent like the last few months implementing that. So, okay, let's go on. All I wanted to do is create the alternate universe. We're not going to use it at the moment. It will just live there and wait. So we go back to our original universe, and now, Mr. President, you have to continue executing. So we go to the next instruction, get a pen from Louise. oops, yeah, risky business. I said it. So let's see, black. Good. The next instruction, get a pen from Dmitry. Great. Let's see. Yes. Then we do the comparison. So let's look at P0 and P1. Is P0 darker than P1?
No.
No. We can move on. Is P1 darker than P2?
Yes.
Yes, okay. So we go to the swap instruction. So please swap P1 and P2. Let's check. Yellow in the middle. Good. So we go to the next instruction. Is P0 darker than P1?
Yes.
Good. So we move to the next instruction. Swap P0 and P1. Great. Now we can check. Yes, it's sorted. Good. So this is deterministic, and that's not always the case. So computers are not fully deterministic, in particular if you have multiple threads, but we have a single-threaded universe here. So now could you please write Uzi with the yellow pen? Good. I was worried it would not be broken, but it is broken, so deterministic. Okay, we get another failure. So that's our failure. And now we need to go back in time. And we've seen before that we cannot do that. But now we have saved the past state in an alternate universe. So now we can say, let's try to somehow execute in reverse with some magic. So maybe we can switch over to President Bacciolini and ask him to execute the program from the current state. And he will be slower because we have to actually create a logbook of everything he does. So it's not a precise clone. It's not that we just copied exactly what President Martinoli was and have that there. But we instrumented this process. So it actually creates a log, which will be very slow, very costly, but we do not care. Because this only happens when there is a problem. And when you have like an atom bomb go off, you're happy to, no, actually you're not happy to wait. But there may be less time-critical problems. So let's jump back in time by doing it this way. So we jump to universe 2. And now could you please, Mr. Bacciolini, go and execute this instruction. So get a pen from Luis and put it in variable P1. If there is anything in there, there's nothing in there. Great. Good. So we are at this state. The next is get a pen from Dimitri and put it in variable P2. Good. So you see, I'm now keeping this log, this record of everything. And this is really expensive, but it's OK. So we go to the condition. Is the pen in P0 darker than the pen in P1? No. Good. We skip to the next comparison. Is the pen in P1 darker than the pen in P0? So is black darker than blue? Yes. So we go to our swap instruction. Could you swap P1 and P2, please? Great. We go to the next comparison. Is P0 darker than P1? Yes. Good. We go to the next swap instruction. Could you swap pen P0 and P1? Perfect. So again, So again, you have a sorted set of pens. The brightest pen is in P0, the darkest pen is in P2. Still bubble sort. Now, could you try to take the pen in P0 and write Uzi on your flip chart? You have a different universe, a different flip chart. Doesn't work? Good. That's also really hard to get this non-determinism replicated, but we're lucky. So now we have the failure. So you can sit down. You're done with your job. Thank you. So now we have the universe replicated, and we have this log in our universe. And we can try to find the root cause of our problem. So This is called following this infection chain. So we can talk like in medicine. We have an infection that started somewhere, and it spread throughout our program, and it led to death, basically, when the program crashes. So let's try to recover that given our log. So we can start, and we say the P0 variable contained a broken pen. Where was this variable last set? And we go back in our log, and we see the yellow was put in there in instruction 11. So you could say instruction 11 is somehow causally related. You may want to fix that. But this doesn't look very important, so maybe that's not the root cause. We could fix it there, but maybe not a good idea. So let's go back. Where did the pen, the yellow pen, come from when it was put into P0? It came from P1. And it was put into P1 in instruction 9, where we swapped P1 and P2. Where did P1's pen come from there? Well, it came from P2. And where was the yellow pen put into P2? In instruction 5. So now we found our origin of the yellow pen. So there is one of my PhD students. I'm really sorry. He is the culprit, the cause of this failure. And that's what you actually do in debugging. You just trace back and you say, I could change this. For example, I could say, whenever I get a pen from Dimitri, I'm first going to check. And if it's wrong, I ask him again. That would be a way to fix it. Or you could now debug Dimitri and look inside him and try to figure the problem. Okay? But he doesn't make any mistakes like that at all. Okay, so the goal of this entire work is to get rid of bugs. And the way we do that in a kind of on a more technical level is called back-in-time debugging. We're debugging, we're going back in time, but we do that only on demand. Only when there is a problem do we pay the price. And the goal is to have that so you can run this in your like normal computer or cell phone, and your cell phone or computer will only run roughly 5% slower. With our universe cloning mechanism that goes on all the time. That's the goal. I think we can reach that. And then when there's a problem, it will go to the cloned universe, and it will start to spend a lot of computation and try to figure out what the problem was, what the cause was of this failure. So you get the full diagnostics, or Apple will get a report, and it will tell Apple exactly the yellow pen came from there. That's the goal. There are quite a lot of research questions when you want to do something like that. On a high level, you could say, where do we create clones? If you followed closely what I did, I just at some point said we clone. But we should pick that carefully. And there are better places and worse places to clone. We can create many clones, not just one. As many as we want, but every clone costs a little bit. We may want to kill clones. I didn't do any killing here. That's not good. But you want to kill clones because a clone uses resources. Even if it's just sitting there, it requires some memory, some state. So you need to kill them from time to time. Then how do you clone? This is in red because this is more of an engineering problem, but a really hairy one. How do you clone things properly? And then in the clone, you produce a log. What goes in this log? What do you do? How do you make it possible to actually log? So if I have President Martinoli and I create a clone, President Baggiolini, there is a difference between them. How do I make them different? How do I mutate them? It's also an engineering question. And there's many other questions. So if somebody is interested in this, please come talk to me or to anybody in my group afterwards. So back to the origin. We have a problem. Software is large and complex. And absolutely, there will be mistakes. We cannot do that without making mistakes. And now I would say our hope is that we can find and fix those mistakes quickly so that they don't cause havoc. That's basically it. I would like to thank a little bit some people, and in particular, my research group. So Milan, who actually sits here, is the first PhD student who graduated out of my group. Dimitri, who is now in London. And then we have Andrea, who gave correct pens. Dimitri, the one with the yellow broken pens. Mohammed, who is cloning the table. And Luis, who also gives out correct pens. So thanks a lot to you guys, because in our faculty, I think often the PhD students do most of the work, and we just sell it. And I also would like to thank a lot Sarah Ambrosini. She's an artist. She created those pictures. I found them on the internet, and I asked her for permission of using them here, so we can actually officially use those for this talk. The nice thing about those pictures are they're all fractals. So they're actually all computed by a computer. She composed them. She figured out the parameters, but they're computer-generated, algorithmic, computational pictures. And I really love them. They're great. And last but not least, I'd like to thank my family, because without them, I wouldn't be here at all. And I think that's my closing slide. You see that if you do informatics, you can do things that physicists cannot do yet. We can do time travel if you want. So if you think about studying something, come study informatics at USI. Thank you.